Welcome to Preparatory Algebra. This first video is intended to be a review about algebraic expressions and sets of numbers. We will be talking about the real number system and all of the subsets contained within the real number system. The real number system evolved over time by expanding the notion of what is meant by the word number. At first, number meant something you could count, like how many cows a rancher owns. These are called the natural numbers, or sometimes the counting numbers. So the natural numbers begin with 1 and continue in a positive direction. 1, 2, 3, 4, 5. These three dots at the end of the pattern are called an ellipsis, and that represents a continued pattern. So 5 would be followed by 6, 7, 8, and so on. At some point, the idea of 0 came in to be considered as a number. If a rancher does not have any cows, then the number of cows that the rancher has would be 0. We call the set of natural numbers plus the number 0 the whole numbers. So whole numbers begin with the natural numbers and include 0. So we have 0, 1, 2, 3, 4, 5, and that pattern also is continued. Now here's a little information about the number 0. What is 0? Is 0 a number? How can the number of nothing be a number? Is 0 nothing, or is it something? Well, we already talked about a farmer having cows versus not having cows. Not having cows would be 0 cows. So if we look at the number 0 again, we know back in history, Arab and Indian scholars were the first to use 0 to develop the place value number system that we use today. When we write a number, we use the numbers 0 through 9. These numerals can stand for ones, tens, hundreds, or other place values. So if we have, for example, 3 hundreds and 2 ones, you'll notice there were no tens mentioned. So it's important to use 3 for the hundreds, 0 for the tens, which means there are no tens, and 2 for the ones. So is 0 a number? The number 0 obeys most of the same rules of arithmetic that ordinary numbers do, and so we do call it a number. It is a very special number. You'll notice throughout the course how we are using the number 0 and how important 0 is. So the only thing that we'll really have to watch out for is knowing that we can't divide by 0. 0 is the additive identity because 0 added to a number will not change the value of the number. Likewise, 1 is the multiplicative identity because multiplying a number by 1 does not change its identity. Next, we'll talk about some negative numbers. Even more abstract than the concept of 0 is perhaps the idea of negative numbers. If, in addition to not having any cows, the rancher owes someone 3 cows, you could say that the number of cows that the rancher owes is -3. It took longer for the idea of negative numbers to be accepted, but eventually they came to be seen as something we could call numbers. The expanded set of numbers that we get by including negative versions of counting numbers is called integers. Here is a list of integers. Integers include whole numbers plus negatives. Again, the 3 dots indicate the pattern continues in that specific direction. So -4 is just the first one in this example I'm showing you, but the negatives would go to -infinity. So we could have -4, -3, -2, -1, 0, 1, 2, 3, 4, and continuing to positive infinity. Here's some more information about negative numbers. How can you have less than 0? Well, if you have a checking account or a debit account, you might know a little something about negative numbers already. So having less than 0 means that you have to add some just to get to 0. So if you spend more money than you have or write a check for an amount more than what you have in your account, you're going to have negative dollars. The strict mathematical definition goes something like this. For every real number n, there exists an opposite denoted as negative n. So there's a minus in front of the number, such that the sum of n and negative n equals 0. Here it is written out in algebraic notation. N added to negative n equals 0. Note that the negative sign in front of the number is part of the symbol for that number. So the symbol negative 3 is one object. It stands for negative 3. The name of the number that is 3 units less than 0. Or you could think of it as 3 units to the left of 0 on a number line. The number 0 is its own opposite. 0 is considered to be neither negative nor positive. The next generalization that we can make is to include the idea of fractions. While it is unlikely that the farmer owns a fractional number of cows, can't really have half a cow, he's not a living cow, many other things in real life are measured in fractions, like a half cup of sugar or a half a glass of water. If we add fractions to the set of integers, we get the set of rational numbers. Rational numbers are in the form a divided by b, where a and b are integers. However, b cannot be 0. We cannot divide by 0. That would be an undefined amount. Rational numbers include what we usually call fractions. So a rational number and a fraction is the same thing. Notice that the word rational contains the word ratio, which should remind you of fractions. The bottom of the fraction is called the denominator. Think of it as the denomination. It tells what size fraction we're talking about, such as fourths, fifths, halves, thirds, tenths, and so on. The top of the fraction is called the numerator. It tells you how many fourths, how many fifths, and so on. There are restrictions to consider. The denominator cannot be 0, as I've stated just a little bit ago. It is correct and okay if the numerator is 0. If the numerator is 0, then the whole fraction is just equal to 0. If I have 0 thirds or 0 fourths, then I don't have anything. However, it makes no sense at all to talk about fractions measured in zeroths. So if I have 0 thirds, that will simplify as 0. If I had 3 divided by 0, that would be undefined, so we're not using division of 0. Fractions can be numbers smaller than 1. For example, 1/2 or 3/4. Those are called proper fractions. If the fraction represents a number larger than 1, such as 5/2, we call that an improper fraction, because 5/2 would simplify to 2.5. That is a number larger than 1. It is still a fraction. It's simply an improper fraction instead of a proper fraction. All integers, remember -4, -3, -2, -1, 0, 1, 2, 3, all of those integers may be written as fractions or rational numbers by simply dividing them by 1. So here we have an example of the integer 3, and that is exactly the same value as writing it as 3 divided by 1, which is now a rational number. So we can take any of our integers, divide them by 1, and now they would be called rational numbers. This means that all the previous sets of numbers, the natural numbers, remember our counting numbers, our whole numbers, which now include 0, and integers, which include the negative numbers, all of those are subsets of the rational numbers. Now, it might seem as though the set of rational numbers would cover every possible case, but that isn't so. There are numbers that cannot be expressed as fractions, and those numbers are called irrational. The irrational numbers cannot be expressed as a ratio of integers. As decimals, they never repeat or terminate. Here are some examples of rational versus irrational numbers. 3/4. Well, it looks like a fraction. If we take 3 and divide it by 4 on a calculator, you will see it terminates 0.75. Since it does terminate, it is a rational number. Another example is 2/3. Take 2 and divide it by 3 on your calculator, and you will see 0.666666, and it repeats. So this value of 6 repeats. That's what the bar represents here. And since it is a repeating decimal, it is considered to be a rational number. Our next example of 5/11. If we take 5 and divide it by 11 on a calculator, you can see that several of the digits, 4, 5, repeat. It's a repeated pattern. 0.454545 and so on. Since it is a repeating decimal, again, it's considered to be a rational number. So 5/11 is a rational number. Try dividing 5 by 7. You'll see that several of the digits in the decimal repeat. So again, we have a rational number. Now we have the square root of 2. It is not written as a fraction, it's written as a radical term. Here you would need to use the function key on your calculator for square root. So depending on your calculator, you might have to enter 2 first and then press the square root function, or some calculators require you to enter the square root function first and then press 2. So when you do that, you will see how the decimal does not have any repeated pattern, and it continues. We've got the 3 dots again. Since there is no repeated pattern and it does not terminate, this represents an irrational number. So the square root of 2 is irrational. Pi is another familiar symbol you might know about. Some calculators have pi that you can press and see also that there's no repeated decimal pattern and the decimal does not terminate. So pi is another example of an irrational number. Here's some more information about irrational numbers. It might seem that the rational numbers could cover any possible number. After all, if I measure the length with a ruler, it's going to come out to some fraction, maybe 2 3/4 inches. Suppose I then measure with more precision. I will get something like 2 5/8 inches, or maybe 2 23/32 inches. It seems that however close I look, it's going to be some fraction. However, that is not always the case. Here's an example. If you draw a line segment that's maybe 1 inch long, and draw another line perpendicular that's also 1 inch long, then connect those lines with this diagonal. This is called the hypotenuse. You will then find that the length of this hypotenuse is the square root of 2. And we just talked about the square root of 2 and how it is an irrational number. The square root of 2 is equivalent to this decimal, and it's been rounded off. And here you can see it into a little greater length. So we cannot represent this hypotenuse by a divided by b because we have a non-terminating decimal. And Pythagoras, more than 26 centuries ago, discovered this notion. In summary, the real number system consists of rational numbers and irrational numbers. All the points on the number line are within the real number system. All possible distances on the number line are considered to be in the real number system as well. When you put the irrational numbers together with the rational numbers, we finally have the complete set of real numbers. So any number that can be found on a number line is considered to be in the real number system. Now here we have an illustration of how all of the subsets under the real number system are related to each other. So if we begin in the center with the natural numbers, 1, 2, 3, and continuing, we go to the next layer, which now includes 0 along with 1, 2, 3, and other positive numbers. The next layer out would be called the integers, which now include negative numbers and 0 and the positive counting numbers. Our next layer out, the rational numbers, include fractions that either have a repeated pattern or they do terminate. Negatives are included. Remember, we can simply divide these by 1 and then they will look like fractions. The same for 0 divided by 1 and all the natural numbers divided by 1. Outside of rational numbers would be the irrational numbers. These are values that do not terminate and do not have repeated patterns. Both the rational numbers and all the subsets under those and the irrational numbers combine to make the real number system. So we will find on the number line all of our real numbers. We can see that there are negative numbers, 0, and positive numbers, and in between these values we find our rational numbers. So in between 0 and 1, if I go exactly halfway, then that would be 1/2. I could find 5/8. I could find 13/7. I could find pi. I'm going to find pi. That is an irrational number. We know that. Square root of 2 we have discussed. And it's about 1.41. So again, that is somewhere in between 1 and 2. So that would be where the square root of 2 is located. And that is just an estimated placement. That is not an exact placement for square root of 2. So every real number corresponds to some distance on the number line from 0. If it is a positive number, it would be found to the right of 0. If it is a negative value, then it is found to the left of 0. And those are the two important points to remember about where values are found on the number line. All of these numbers are considered to be a distance from 0. Now let's practice the concepts that we've just talked about, considering the real number system, and we are given elements of the set, and we're going to determine which of these elements, if any or all, would be found in the whole number category or subset. We have the numbers 12, 0, square root of 11, square root of 81, 3/5, and negative 203. So under the whole numbers, remember these are numbers that begin with 0 and go in the positive direction. 0, 1, 2, 3, 4, 5, and so on. So it looks like definitely 12 would be considered a whole number. 0 is actually the first value in the subset of whole numbers. Now I don't think any of us have memorized what the square root of 11 is, so this is where your calculator would be helpful. And you will find that the square root of 11 is a non-terminating decimal and it is not a repeated pattern. So we can't consider square root of 11 as a whole number. Square root of 81. Now some of you actually might know that that simplifies as 9. If you didn't remember that, then simply find the square root of 81 with your calculator. So 9 is a whole number. 3/5. Take 3 and divide that by 5. That is not going to divide evenly, and therefore it's not going to turn out to be a whole number, so we can't include that. Negative 203. It looked good, except there is this negative in front, and negative numbers are not whole numbers. So we only have 12, 0, and 9 for whole numbers. Next, integers. Integers include all of the whole numbers. So automatically, I know that 12, 0, and 9 need to be included in the integers. Now let's consider the other values that we haven't written in our list. Square root of 11 was the non-terminating decimal, so that is not an integer. 3/5, that is also going to be some decimal amount, so that is not an integer. Negative 203. This is going to be included in the integers because the integers include negative values. So negative 203 is included for integers. Natural numbers are the counting numbers, beginning with 1. So just looking back to the integers, we know that 12 is a counting number. 0 is not included with the natural numbers. Natural numbers begin with 1. 9 is acceptable, but negative anything is not going to be a natural number. So we only have 12 and 9. And for 9, I really should be writing that as square root of 81. Let's go ahead and fix that, square root of 81, so we don't get mixed up here. Okay, rational numbers. Those are fractions or numbers that could be written as fractions. So although 12 does not appear to be a fraction, remember we can take any integer and divide by 1, and then it is written as a rational number. So 12 is a rational number. 0 can be divided by 1. So 0 is a rational number. Square root of 11 is not included because really we're just looking back at our list of integers. And since square root of 11 wasn't included there, it can't be included with our rational numbers. Square root of 81 was included with the integers because that simplifies as 9. 9 can be divided by 1. So square root 81 is a rational number. Negative 203 could be written as negative 203 divided by 1, so that is also a rational number. Now let's look back to the original list, and you will see that 3/5 already is written as a rational number, so don't forget to include 3/5 with the rational numbers. Irrational numbers are the non-terminating, non-repeated pattern decimal values. So that would not be 12 or 0, but square root of 11 we found does not have a repeated decimal or terminating decimal. Square root of 81, that was 9, that terminates. 3/5 terminates, and negative 203 is an integer that is not an irrational number. So only square root of 11 is the irrational number. Real numbers. So hopefully it doesn't take too much thought to list the real numbers, because the real numbers include all of the subsets we've just talked about. They include irrational numbers, they include the rational numbers, and within rational numbers we have our integers, whole numbers, and natural numbers. So it should be every number listed in the set of elements. So we have 12, 0, square root of 11, square root of 81, 3/5, and negative 203. Here's one more example. We have a list of the elements of the set: 5, 31, square root of 17, square root of 100, 9 halves, 1 half, 1/7, pi, -100, and 8 halves. So let's look down the elements again. 5, 31, square root of 17. You might want to try that out on your calculator, and you will find that the square root of 17 is a non-terminating, non-repeating value. So we know right away that square root of 17 would be an irrational number. So I'm going to list that right now. Square root of 100. On your calculator, you will find that that is equivalent to 10. So that's going to fit in several of our subsets. We'll get to that in a minute. 9 halves. We can see right away it is written as a rational number. 9 divided by 2 is 4.5. So that is a terminating decimal. We'll find that useful. 1 half. 1/3 is 0.33333, so that's a repeating decimal. 1/7 you will find has several values to the right of the decimal that repeat. So that is also a repeated pattern. With pi, you probably remember we talked about pi, and that is a non-terminating decimal. -100, and then 8 halves. 8 halves reduces to 4, so that does terminate. Now let's go back to the first subset, whole numbers. Remember, whole numbers begin with 0 and then the counting numbers, 0, 1, 2, 3, and so on. So we'll need to include 5, 31 is a counting, 31 is a whole number. Then we'll go to square root of 100, because we know that's worth 10. Anything written as a fraction is not going to be a whole number, so we can bypass those three. Pi is a non-terminating decimal, so that isn't a whole number. -100 has a negative with it, so that is not a whole number. However, 8 halves reduces to 4, so 8 halves would be included with whole numbers because it is equivalent to 4. Next, the integers would include all the whole numbers we listed and any negative values. So I'm starting with 5, 31, square root of 100, 8 halves, and we also can include now the -100. With the natural numbers, these are the counting numbers beginning with 1. So that would include 5 and 31. Square root of 100, remember, is 10. So we'll keep our square root of 100. 8 halves is 4, so that would be a counting number, but not the negative value. So 5, 31, square root of 100, and 82. So you might notice here that the whole number list and the natural number list are the same because we didn't have 0 given as an element. Rational numbers can be written as fractions. So any integer can be written as a fraction. So I'll start with all of the integers we've already listed. 5, 31, square root of 100, 8 halves, -100. And now we'll go back and look at the elements and see if there are some written already as fractions. So we pick up 9 halves, 1/3, and 1/7. The irrational numbers, we already talked about square root of 17. Are there any others? Looking down the list of elements, here's pi. That is a non-terminating decimal value, so we need to include pi. Real numbers. Real numbers consists of all the irrational numbers, all the rational numbers, whole numbers, integers, natural numbers. So it is going to be every one of these elements in the set. So I hope you found this video about the real number system helpful.